All right, let's crack the code on some of the biggest buzzwords in tech today: AI, machine learning, and deep learning. You've probably heard these terms thrown around everywhere, right? On the news, in your apps. But what do they actually mean? And more importantly, how do they all fit together? Well, that's exactly what we're going to break down. And to make this super clear, we're going to use a really simple but honestly a perfect metaphor. Think of a set of Russian nesting dolls. You'll see how each of these big ideas fits neatly inside the next, starting from the outside and working our way in. Okay, so here's our game plan. We'll start with the big picture, then look at a simple recipe for machine learning. After that, we'll see what happens when you go from shallow to deep, how these machines actually learn, and we'll wrap it all up with the one key takeaway you won't want to forget. All right, let's get started. Time to open up that biggest, outermost doll: artificial intelligence itself. So, artificial intelligence, or AI, it's not really one specific thing. Think of it as this giant umbrella, the whole field, covering any and every method that helps a computer act with human-like intelligence. Things like reasoning, making decisions, that kind of stuff. Okay, now for the fun part. Let's open up that AI doll. What do we find inside? Machine learning. And this is where things get really cool. See, instead of a programmer writing out every single rule by hand, ML is a specific branch of AI where we just give the machine a ton of data and let it figure out the patterns all by itself. And nested right inside of machine learning, you've got neural networks. You can think of these as the engine or even the brain of the whole operation. They're these computational systems that are actually inspired by how the neurons in our own brains are all connected. This is what does the real heavy lifting. And that brings us to the very center, the smallest, but in many ways, the most powerful doll in the set: deep learning. This is basically a supercharged version of machine learning. It uses those neural networks, but with lots and lots of layers stacked on top of each other. That's where the deep part comes from. And it's this depth that lets it handle really complex, messy stuff like images, sound, and human language. So that's the hierarchy. But how does a basic machine learning model actually, decide something? Let's use a super simple, relatable example. Imagine we're building a model to answer the most important question of the day: should you order pizza tonight? First things first, the model needs some information. We call these inputs, and they're just real-world questions turned into numbers. So for our pizza problem, we could ask, will ordering pizza save me time? Is it a cheap dinner option? Is it healthy? A yes becomes a 1, and a no becomes a 0. Simple as that. But here's the thing. Not all of those questions are equally important to you, right? Maybe saving time is your #1 priority, but you're not too worried about the cost. To account for this, we give each factor an important score. We call these weights. From there, the machine just does some really basic math. It takes each input, our 1s and 0s, and multiplies it by its weight. So, time saved was a yes, that's a 1. And since you really value your time, its weight is a 5. 1 times 5 is 5. Healthy option was a no, a 0. So it doesn't matter what its weight is, the score is 0. Then you just add them all up, and in this case, we get a total score of 9.
Okay, last step. We take that total score of 9 and we compare it to a preset limit, a threshold. Let's say our threshold is 7. Is 9 bigger than 7? You bet it is. And just like that, the model makes its prediction. It's pizza night. That's it. That's the fundamental logic at play here.
So now that we have that basic recipe down, let's look at how we get from that simple decision to the mind-blowing power of deep learning. What's the real difference here?
This table lays it out perfectly. There are really 3 big distinctions. First, layers. Traditional ML is shallow. It only has a few. Deep learning, as the name suggests, has a lot more. Second, the human role. With ML, a human often has to point out the important features in the data. But with deep learning, its depth allows it to find those features all on its own. And that leads to the third point, data type. Because DL can find its own features, it's amazing at handling raw, messy, unstructured data. Think images, audio files, you name it.
Okay, so we get the structure now. But how do these models actually learn? How do they go from being a blank slate to making really smart predictions? Well, there are 2 main ways this happens. The first is called supervised learning. This is like giving the model a textbook with an answer key in the back. You feed it tons of data that's already been labeled correctly by humans, and it learns by checking its work against the right answers. On the other hand, you have unsupervised learning. This is more like giving the model a giant library of books with no instructions and just telling it to find the patterns. It has to figure out the hidden structures all by itself, without a teacher. And a really critical part of this learning process, especially in deep learning, is something called backpropagation. It sounds complicated, but the idea is pretty intuitive. After the model makes a guess, it looks at how far off it was from the correct answer. Then, it sends a signal backward through the entire network, adjusting all those little weights we talked about, basically telling each one, hey, you are a little bit responsible for this mistake, so tweak yourself just a tiny bit. It's literally learning from its mistakes, over and over, getting a little smarter each time.
So after all of that, what's the one big idea you should walk away with? What's the main takeaway here?
It really comes down to this trade-off. The key distinctions are all linked. You have structural complexity, just the number of layers. That complexity changes the level of human dependence. The more layers, the less a human has to guide it. And that, in turn, changes the data requirements. Simple ML can work with smaller, cleaner data, but deep learning absolutely thrives on massive, raw datasets. So the ultimate takeaway is this. Moving from ML to DL is really a trade between needing a human in the loop and giving the machine more autonomy.
And that leaves us with a really fascinating final thought, doesn't it? As these deep learning systems get more and more autonomous, more capable of learning things on their own without our help, what does that mean for the future role of human experts? Where does human creativity and intuition fit into a world where machines can learn so much, so fast, all by themselves?